This is my lab 2 motion of a falling object. The lab is to analyze the motion of a falling object dropped from rest. The observed motion will be compared to two computational models, one with the effect of the drag force and one that does not have it. And both models include gravity. The system of the experiment is the ball of paper, and the surroundings are everything else around it. This lab will help to demonstrate the principles of Newton's second law and the effects of the drag force. In this experiment, the main result that we gain is the object undergoes uniformly accelerated motion due to gravity, and further help us understand the effects of drag force. The fundamental principles that we use are Newton's second law, which is a system change in momentum is proportional to the net force applied, and we use this to derive our velocity update formula. And a gravitational force, which is Fg equals mg, which is the attractive force that pulls objects with mass toward each other. We also use drag force, which is the resistive force that opposes the object's motion. And here are all the important derivations and formulas that we use. Some more important concepts are the iteration process and the kinematics. Both are used heavily in our calculations and computation. The ball was thrown from a height of 1 meter and was recorded all the way to the moment it hit the ground. Then the video was put into tracker and the data points were tracked to gather observational data. On the top picture, you see the path that the ball or the paper ball took, and it looks like it falling from rest and reaching all the way to the ground. Now, if you look at our graph, it looks a little peculiar, but that's because the way the axes were aligned, and that was the result of that error. However, if you were to flip the graph, it would result in a projectile motion graph that we're more familiar with. However, that's not the case. Now, when it comes to the computational model with gravity only, our initialization factors are the ball's mass is 1, the position vectors taken from the original and observational data that we had got, and then velocity was calculated using the observational data, and we have our time step to be 0.001 to be much more accurate than our observational data, and we have g to equal 9.8. And then in our calculation model, in our actual calculation loop, we defined F gravity and calculated it. Remember, we used F equals mg, and it's downward, so it's negative in the y direction. And then we set F net to equal 0. Remember, force is constant, and that's the way the y matters comes into here. We then used Newton's second law to derive our velocity update formula, and then we used the kinematics equation to update our position, and we used the kinematics equation because force is constant. Now, when it comes to our computational model with gravity and drag, our initialization factors are the same. However, we do have b, which is our drag coefficient, which is 0.1, and in our calculation loop, we took it a step further and calculated for F drag, and we calculated for the magnitude of speed, and then we calculated the velocity unit vector, and we compiled those and multiplied it by the negative of the b coefficient, or the drag coefficient, to get F drag, and we included F drag into our F net, and still we use the same initial velocity update formula and the position update formula that we used in our gravity computational model. Now, these are 3 separate graphs, but the first graph is the observed data, and if we were to flip this around, you can see that it holds a much better and closer shape to the y position with gravity and drag. And when you compare the y position with gravity, this is the model with only gravity. This is more of a very flat model compared to the y position with the gravity and drag model. Observed data is less accurate because of the data points that were taken by hand, while gravity and drag models are computationally calculated. So possible errors that we could have are outside forces. We did do this in an outside setting where people are walking by, and the ball shape is another important factor because this was a crumpled up piece of paper and not a perfect sphere, so it has ridges and imperfections. The third and important one is probably the position tracking. The tracking data was done by me, a human. The axes that were used were not lined up in the most effective way, though essentially it did seem like that was the right track. But we now know the effect of that. Rightmost one shows a linear decrease in velocity, but if you look at the one with the left, looking at the model with both gravity and drag, it presents a nonlinear change as it plateaus over time. Hence, it's more of a better prediction of terminal velocity if we were to consider which model predicts a more terminal velocity. The same initial speed as our original experiment, the total time to reach the ground would be much longer than our original case where it was launched at an angle. The left derivation is when it was thrown straight up. The right derivation shows our original case. And it looks as if it's the same thing in the same derivation steps. However, the only thing that changes is our sign on our our sine theta that is included in our original experiment, and that reduces the number of time because sine itself is a number that oscillates between 0 and 1, and the calculations would include a lesser number in our original time of its track. Able to watch an object at rest fall and observe its track. Then we provided two different computational models that assisted in showing more of an accurate version of the concepts of Newton's law, gravity, and drag. Thank you.